Hi, this is a video to help you through the activity on properties of matter. I'd like you to start out by looking at the table on the first page of your activity and answering the first three questions using your experience and the information in the table. In particular, the information on density would be useful. So please pause the video and try at least the first three questions on the first page of your activity. All right, let's talk about this now. From your experience, you probably remember that ice floats on top of water, no matter what size the glass of ice water is, or even a whole ocean with ice on the top of it. Ice floats on water because it's less dense than water, and you can tell this from the table that's in front of you. So water has a density of about 1 gram per milliliter when it's liquid. On the other hand, when it's solid, it has a lower density of about 0.9 grams per milliliter. This slightly lower density of ice is enough for the ice to always float on top of water, and it has enough buoyancy for a polar bear to stand on top of it. Anything that is less dense than water will float. Corks float on water, and so do pieces of wood. Here's a picture of a piece of wood floating on water, and it's a piece of pine wood. Pine has a density of 0.5 grams per milliliter. Because it has a lower density than water, it will always float on top of water. On the other hand, things that have a higher density than water will always sink. Here's an example of a lead bar at the bottom of a cup of water. The lead has a density of 11 grams per milliliter. This is much higher than the density of water, and so the lead will sink. Let's look again at this table. Make sure you notice that this row here is talking about solid water at freezing temperatures, 0 degrees Celsius, whereas this is liquid water. So in the first column, you have a list of different materials, and in the second and third columns, you have the mass for a specific volume of that material. And then density is listed in the last column. Notice that if we take the mass divided by the volume, you'll get the density. And density is simply mass divided by volume. Most of the time, the density is given in units of grams per milliliter. So unless specified otherwise, expect that density is reported in grams per milliliter. Please note the formula for density on number 4 in your activity. To do question number 5, there is one unit conversion that you should know. And that is that a cubic centimeter is basically a cubic volume of 1 centimeter by 1 centimeter by 1 centimeter. So it's 1 centimeter cubed, and it's also called a cubic centimeter and represented with a cc. 1 cubic centimeter is the same as 1 milliliter. This is a unit conversion or an equivalent unit that you could use in dimensional analysis, and you will need it for solving problem number 5. So at this point, you can pause the video and solve number 5, and then we can go over it together. Number 5 is asking you to solve for the density of a bar of soap, given the mass of the soap in grams and the volume in cubic centimeters. And it's asking you if the soap will float on water. If you know the density of the soap, then you will be able to answer the second part of the question. Remember, density is equal to the mass over the volume, and we're given the mass of the soap and the volume of the soap in cubic centimeters. The mass is 90 grams, the volume is 100 cubic centimeters, and we know that 1 cubic centimeter is the same as 1 milliliter. When we answer the question, we'll want to give our density in units of grams per milliliter. So let's start. Density is going to be equal to the mass of the soap divided by its volume. You can use the equivalent unit 1 cc is equal to 1 milliliter to do a unit conversion using dimensional analysis. This will allow you to cross off the unit cubic centimeter and get your final answer in grams per milliliter. The answer is 0.9 grams per milliliter. I've reported this in one significant figure. And this tells me that the density of my soap is less than 1. 1 gram per milliliter is the density of water. So if my soap is less dense than water, the soap will float on the water. Now feel free to pause the video and try number 6, and then we can do it together. Number 6 gives you the density of a patient's blood and asks you how much his donation weighs if he's donated 470 milliliters. For this problem, you can actually use the density just as if it's an equivalent unit. The blood density is 1.06 grams per milliliter, and that means that 1.06 grams of this person's blood is equal to 1 milliliter of their blood. Since the volume is 470 milliliters, we can calculate the mass using this equivalent unit, which allows us to convert between volume and mass. So we start out with the volume of the person's blood, and we simply cancel out our milliliter unit, and we're left with the number of grams of blood. I'm going to report this answer in 3 significant figures because I have 3 significant figures in both of the operands that I started with. 498 grams of blood is the answer. Now you've seen a problem in number 5 where you've solved for density, and you've seen a problem in number 6 where you used density as a unit conversion. There are some more practice problems in the end of your activity in the check for understanding. Now let's switch gears and talk about temperature scales. Here's the figure that's in your activity, and it's showing the 3 different temperature scales. The Fahrenheit scale is what you're used to. Celsius scale is what is used in the metric system, and Kelvin is what scientists use. Notice that the boiling point of water is listed on each one of the scales, normal body temperature is listed on each one of the scales, and the freezing or melting point of water is listed on each one of the scales. The other relevant piece of information is the difference between the freezing point and the boiling point of water. There's 100 Kelvin between these 2 points, 100 degrees Celsius between these 2 points, and a 180 degrees Fahrenheit between these 2 points. Pause the video now and answer the questions on the first page of this activity. For the answer to number 1, hopefully you can see that normal body temperature in degrees Celsius is 37 degrees. 37 degrees Celsius is normal body temperature, just like 98.6 degrees Fahrenheit is normal body temperature. The second question asks you the difference between a Kelvin and a degree Celsius. And to answer this question, notice the difference, or notice how many kelvins and Celsius are in the same space of temperature, or the same difference in temperature. 100 Kelvin degrees is the difference between freezing and boiling of water, and 100 Celsius degrees is the same amount. So 100 Kelvin degrees is equal to 100 Celsius degrees. Therefore, Kelvin is exactly the same size as Celsius. The main difference is that the scales are skewed by 273 degrees Celsius. So at 0 degrees Celsius, it's 273. Anytime you need to find a Kelvin degree, you just add 273 degrees to the Celsius degree. Now I'd like you to turn the page and try number 4. Notice that there are 100 Celsius degrees in the same difference in temperature as 180 Fahrenheit degrees. So 180 Fahrenheit degrees is equal to 100 Celsius degrees. If it takes less of the Celsius degrees to span the same temperature, that means the Celsius degrees must be larger because you can fit less of them in the same space. So a Celsius degree is larger than a Fahrenheit degree. The relationship between Fahrenheit and Celsius can be found by just dividing one by the other. So if I put 180 degrees of Fahrenheit divided by 100 Celsius degrees, I would get a relationship of 1.8 degrees Fahrenheit for every degree Celsius. If I put this in common terms, I would say that Celsius is 1.8 times larger than Fahrenheit. In order to convert between degrees Celsius and Fahrenheit, there are formulas you can memorize, or if you conceptually understand this, you don't have to memorize anything. For example, what if you had a temperature in degrees Fahrenheit and you wanted to convert to Celsius? Let's look at the temperature scales here. If you were given a temperature in degrees Fahrenheit, like 32 degrees Fahrenheit, you would subtract 32 from that number to get the same degree Celsius, because 32 is the same as 0. So I can write a formula here, and this is what number 5 is asking you to do. You can say that the degree Celsius is going to be equal to the temperature in Fahrenheit minus 32 degrees of Fahrenheit. Now, that will not always give you the right answer unless you're at 0 degrees. Notice that I can't simply subtract 32 from body temperature and get the correct answer. So there's, because the Fahrenheit degrees and the Celsius degrees are different sizes, you have to do a conversion. And you can use this equivalency as a conversion. You could use 180 and 100, or you can use 1.8 and 1. In my slide, I've used the 1.8 and 1. So the degree Celsius here equals some kind of temperature in Fahrenheit units, but then I want to convert to Celsius units. So I'll use this equivalency. And I put Fahrenheit in the denominator so that my Fahrenheits will cancel and I will get my answer in degrees Celsius. Using this formula, try to solve number 6 and check the key to make sure that you're correct. Number 7 is asking you to write an equation to convert degrees Celsius to degrees Fahrenheit. Or in other words, if you were given a temperature in degrees Celsius, how would you get that temperature into degrees Fahrenheit? Degrees Fahrenheit is going to be equal to the temperature in Celsius. You'll have to convert it to degrees Fahrenheit units and then add 32. This is the formula that you should put in number 7. For either of these pink fractions, you could either use the one shown or you could use the 100 degrees Celsius to 180 degrees Fahrenheit ratio that is represented by this equivalency. Now you should try to solve number 8 and check the answer key to make sure that you're correct. All right, let's switch gears one more time and talk about energy. Energy is what makes the world go round. There's energy in the sun in the form of light. There's energy in these windmills in the form of motion. And there's energy in the flowers in the form of stored energy. There are 2 types of energy that you should know about. The first is potential energy. And potential energy is the stored energy. It can be, it's basically anything that's still is usually said to have potential energy. And it's, a ball that's maybe very high up in the air or resting on a high place. It has potential energy because the energy can be released when it falls. The kitty in this picture has a lot of potential energy. It's up in a tree very high, and the energy is stored. It would only be released if the cat fell down, and the falling would be a different kind of energy called kinetic energy. Another type of stored energy is an elastic potential energy. Anytime when there's force applied against gravity or against a force, it's potential energy. Potential energy can also be stored in chemical bonds. So molecules have energy stored in their bonds, and that is potential energy. The other type of energy is kinetic energy. So this is the energy of motion. If the cat falls down from the tree, as it's moving, it has kinetic energy. If this person would release a ball from a slingshot, as the ball is moving through the air, it would have kinetic energy. And energy can be released from chemical bonds through chemical reactions. As bonds are broken, they usually release heat energy, and that energy is kinetic energy. So you should know the difference between potential and kinetic energies. We're also going to want to know the units for energy so that we can use dimensional analysis to do unit conversions. And the energy units you should know about are the calorie and the joule. So calorie is the unit in the English system that we use for energy, and 1 calorie is equal to 4.814 joules. Joules is the unit of energy for the metric system. Now notice that this calorie here has a lowercase c. Sometimes you'll see a calorie with a capital C, and this is a different kind of calorie. Here I've written calorie with a capital C, and its abbreviation is a capital C-A-L, cal. One of these calories is different than this calorie. And in fact, a capital C calorie is something that we call a nutritional calorie. It's actually 1,000 of the regular English unit calories, or the lowercase c-a-l. This is very confusing, unfortunately. But this is something that the nutritional industry or the food industry has done to us. In the United States, anytime you see calories on the outside of a food container, these are nutritional calories, and they're actually equal to 1,000 of our regular calories, or 1 kilocalorie. So keep this in mind and be careful about the way that you're writing calorie. Now I'd like you to read through the energy part of this activity. Make sure you can answer the questions. Once you finish the activity, make sure you also complete the check for understanding questions to ensure that you have a thorough understanding of this material. Then move on to the next activity, balancing chemical equations. Hi, in this video, I'm going to teach you how to balance a chemical equation, and this is to help you go through the activity on balancing chemical equations. Let's remind ourselves of how chemists write chemical changes. There's always an arrow to show the change, and you have on one side of the arrow the reactants, or what you're starting with, and on the other side of the arrow you have your products, or what you end up with. So I've written the same chemical equation in 2 different ways here. I've written a cartoon version where I have solid carbon, oxygen molecule, and I get carbon dioxide in the end. The word heat over this arrow is just telling me that I have to heat the reaction in order for this change to happen. So once again, on this side I have reactants, then I have my reaction arrow showing my change. Sometimes there's something over the reaction arrow, and that is usually a catalyst, something that just helps the change happen. And then my products over here on this side. To balance a chemical equation, you essentially want to make sure that there are the same number of each type of atom on the reactant side and the product side. So now let's count. This table is to help you keep track. In the reactant side here, how many carbon atoms are there? Well, either way you look at this, if you look at the chemical formulas or the cartoon, you can see that there's only 1 carbon on the reactant side. In the products, there's also only 1 carbon. Here, carbon in this carbon dioxide, or here in this molecule, the cartoon. Now I'm going to count the number of oxygens. You can see that there are 2 oxygens on the reactant side and also 2 oxygens on the product side. Now you want to compare reactants to products and make sure that you have the same number of each type of atom on the reactants and the product side. Because there are the same number of all atoms on the reactants and the product side, this equation is balanced. So you don't have to do anything. Now let's look at another example. I'm going to count the atoms. These are the steps that you'll want to use whenever you're trying to balance a chemical equation or just determine whether it's balanced. You count the atoms and see if it's balanced. On the reactant side of this equation, you can see that there's 1 carbon, 4 hydrogens, and 2 oxygens. On the product side, there's 1 carbon, 3 oxygens, and 2 hydrogens. So notice that we don't have the same number of all of the types of atoms on the reactants and the products. So after we count the atoms, we can determine whether the reaction is balanced, and this one is not balanced. When you have to balance an equation, the first thing you should do is balance the things that appear only once on either side of the equation. The last thing you want to do is balance the oxygens and the hydrogens. So let's look. Balance the things that appear only once on either side. And that means, for example, carbon here appears only once in one of the reactants, and it only appears once over here. Oxygen, on the other hand, appears only once on this side, but it appears twice on the product side. So I would balance the carbons first because they only appear once, and they're already balanced. And then I want to look at the hydrogens. Hydrogens also only appear once. And the next thing I'll do is balance those hydrogens. So since there's 4 hydrogens over here and only 2 over here, I can put a 2 in front of the water, and now I've multiplied this whole thing by 2. So now I'm going to recount. I can see that I've changed the number of hydrogens, but I've also changed the number of oxygens. And now I can see that my carbons are balanced and my hydrogens are balanced, but now I need to balance my oxygen. And I'm lucky because I can do that by balancing oxygen over here. If I put a 2 in front of this one, then I end up with 4 oxygens, and I haven't changed the number of any of my other atoms. The last thing you want to do is recheck, recount those atoms and make sure they are in fact balanced. Let's try another example. First, count the atoms. On this reactant side, you have 1 iron and 2 chlorines. And on the product side, you have 1 iron and 3 chlorines. Balance the things that appear only once. Well, everything appears only once. So what we'll do, let's see, the irons are already balanced, so let's make the chlorines balanced. All right, so I see that I have 3 chlorides over here and 2 chlorides over here. And so what I do is I'm going to take, basically, I'll probably multiply this side by 2. And if I do that, then I'm going to change the numbers of total atoms. So I've increased both the number of iron and chloride on the product side. So now I'm going to try to make the things over here match what I have over here. I can do that by putting a 2 in front of the iron. Now I have 2 irons, and that balances. And now I can balance the chlorines by putting a 3 in front of the chloride molecule. That gives me 6 chlorides. Then I check. And in fact, I have balanced my equation, and I'm done. Now, the best way to learn how to do this well is to practice. So please stop. So the video is over now, and it's up to you. Work your way through the activity and check your work. If you need help, come find help. Either come to my office hours or ask a friend. Make sure that this makes sense. It can be fun and easy after some practice.